Hello all, I Daksha Patel from Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. I am working as an assistant professor in computer department. Now, today we are going to learn about unit number 2, which is analysis of algorithm. The topic to be covered in unit number 2, that is analysis of algorithm, how to define the efficiency of algorithm, how to analyze which one is the average case, which one is the best case and which one is the worst case. And we also studied asymptotic notation, which is used for comparison between different algorithm, and study analyzing the control statement. Using analyzing the control statement, we come to know what is the time complexity of algorithm. After that, we study the sorting. What is the sorting? Sorting algorithms that include the different techniques, that is bubble sort, selection sort, insertion sort, cell sort and heap sort. And also study the different sorting, which is take the linear time to execute, that is bucket sort, radix sort and counting sort. And last we study the amortized analysis. Now first of all we see analysis of algorithm, in which we see what is the analysis of algorithm and why analysis is required. What is the analysis of algorithm? Analyzing an algorithm means we calculate or predict the resources that algorithm require. Now which type of resources is required for analysis? That is two most important resources. The first is a computing time, which is known as a time complexity. Now how to define the time complexity? Time complexity of an algorithm means the amount of time taken by an algorithm to run. Second important resource is that is storage space, that is known as in space complexity. Now what is the space complexity? That is the amount of the space taken by an algorithms, that is known as in space complexity. Now why analysis is required? After analyze the problem, we come to know which one is the most efficient, which can be easily identified after defining the time complexity of algorithm. By computing the time complexity, we come to know whether algorithm is slow or fast. And by computing the space complexity, we can analyze whether an algorithm require more or less space. Now which type of analysis is done? There are two type of analysis, that is empirical and second one is a theoretical. In the empirical approach, the programming different technique is used and running them into the various input using computer. While in theoretical approach, we determine the mathematical statement and analyze them. In empirical approach, implementation of different technique may be difficult, but in theoretical approach, we use the algorithm instead of implementation. While in empirical approach, the same hardware and software environment must be used for comparing the two algorithms, where in the theoretical approach, the speed of an algorithm can be determined independent of hardware and software requirement. Now, in the empirical approach, the result may not be indicative of the running time on other input not included in the experiment. While in theoretical approach, the characterized running time is a function of input size and it considered all possible value. So, in this way, we can analyze the problem. Now, what is the problem and instance? Now, what is instance? Instance of a problem consists of input needed to compute the solution of a problem. For example, the statement is written like multiply the two positive number, that is known as a problem. But for multiplying the two positive number, we need some integer number. For example, 981 and 1234, that is known as an instance. Now what is the size of instance? Size of instance is any integer that is number of component in an instance. For example, we take the sorting problem. Now, in the sorting problem, what is the instance size? That is the number of element to be sorted. Now, if we take the graph problem, now what is the instance size of graph problem? That is the number of nodes or edges or a boat. That is known as an instance. Next, efficiency of algorithm. Now, efficiency of algorithm is measured of the amount of resources consumed in solving a problem of size n. The two most important resources are time complexity and space complexity. To measure the efficiency of an algorithm, to measure its time complexity by using the following approach. First, to run it and measure how much processor time is needed. And second thing, that is mathematically computing how much time is needed is the function of input size. Now next, efficiency of algorithm depends on input size and nature of input. For example, the size of input. If we take sorting of 100 number, we will take the less time than sorting of 10,000 numbers. So running time of an algorithm is usually measured as a function of input size. In theoretical computation of time complexity, running time is measured in terms of number of steps or primitives operation performed. Now we take the here one of example for linear search. Now how it is work? Suppose there is one jar is given. In jar contain the sum of business card. Now you have to ask to determine whether the name of Asymptotic is in the jar. To do this, you have to decide simply go through all the cards one by one. Now search is the all the card one by one. It is the name contain Asymptotic or not. And now how much time is taken? It can be determined how many cards are in the jars. Depends on the size of input. Now linear search is the method for finding the particular value from the given list. The algorithm check each element one at a time and in a sequence until its desired element is found. Linear search is the simplest search algorithm and it is the special case of brute force search. Now here we take the another example for linear search in which some array is given. Array must be in which we have to search 1 4 in the given array. Now for doing this we have to compare the all value of array with given key element. Now comparing the value of I index with the given element one by one until we get the desired element or end of the array. Now in the first step we compare the value at index 0, I equal to 0, value is 2, 2 is not equal to 1. So we increment the value of index, that is I equal to 1. The index 1 contain the value 9 which is not equal to 1. Now we increment the index value. So I equal to 2. Index 2 has in value 3. So 3 is not equal to 1. Again we increment the index value. That is I equal to 3 and index 3 at index 3 the value is equal to 1. So at index 3 we find our desired value, that is 1 equal to 1. So in this way linear search is work. Now here we write the algorithm for linear search. It takes the input as an array element and output, that is return the index at which the desired element is found. If element is not found, then it returns the -1. Now algorithm for that for I equal to 1 to last index of A, if A of I is equal to element, then return its index, otherwise it return -1. Now here we found the how we can say which one is the best case, which one is the average case and which one is the worst case. To require element in the given array can be found at the tree position. It may be in first position, it may be anywhere after the first position, or it may be a last position, or it may not found at all in the given array. Then if element is found at the first position, means minimum comparison is required, which is known as in base case. If element is found after at the first position, means average number of comparison is required, which is known as an average case. If element is found at the last position, means maximum comparison is required, then it is known as in worst case. Or if it is not found at all in the given array, means maximum comparison is required, which is known as in worst case. Here we given some graphical representation that if element is found at the first position, then it is known as in best case. If it is found between after first position and before last position, then it is known as in average case. If it is found at the last position or it is not found anywhere in the given array, then it is known as in worst case. Now analysis of algorithm has a three case: base case, average case and worst case. Now when we say the given algorithm is a base case, if it has resources use is minimum, algorithm behavior under optimal condition, minimum number of steps or operation is required, lower bound on running time, then it is known as in base case. Now when it is known as an average case, if resources use is average, algorithm behavior under random condition, average number of steps or operation is required, and average bound on running time, then it is known as an average case. Now when it is known as in worst case, if resources use is maximum, algorithms behaviors under the worst cases condition, maximum number of steps or operation is required, and it bound on upper bound on running time. In that case, we can say the algorithm in worst case. Now generally base case is not occur in real life, but average case and worst case performance are the most used in the algorithm analysis. Now second thing, that is asymptotic notation. Now what is the asymptotic notation? Asymptotic notation is used for comparison between the two algorithms. There are three notation is used, that is big O notation, omega notation and theta notation. The first is a big O notation, omega notation and third is the theta notation, which analyze the algorithm running time. It is also known as an algorithm growth rate. Now, asymptotic notation are used to characterize the complexity of an algorithm and also to compare the performance of two or more algorithms which are solving the same problems. Now, here we take the example for asymptotic notation. For solving the problem P, we have a two different algorithms, that is A and B. For solving the same problem P, we have a two algorithm A and B. We say that algorithm A is a big O of B, means A is less or equal to B. If algorithm A is equal to omega of algorithm B, means A is greater or equal to B. Omega provide the upper bound. Sorry. Big O notation provide, here big O notation provide upper bound, omega notation provide lower bound and theta notation provide equal bound. Now if we say A is equal to theta of B, means A is equal to B. Now here we take another example, that is parent child relationship. If we write parent is equal to omega of CH, means parent is greater or equal to CH, that is true. If we write child is equal to omega big O of P, then children is less or equal to P, which is also right. But if we write child is equal to omega of parent, then it is false, because child is greater than parent, which is false. Now we understand it by using the function. Let there is a two function f of n and g of n be a two non-negative function. Non-negative function means positive function. Now which one is known as a positive function? If we write n minus 100, then it is known as a positive function. But if we write 100 minus n, then it is known as a negative function. And here n0 and some constant are used, which is some integer number, and n0 is greater than n is greater than n0 and c is greater than 0. Now g of n is asymptotically upper bound of f of n. We represent in notation here f of n is equal to big O of g of n, implies that f of n is lesser equal to c into g of n. Here we use some graphical representation that f of n is equal to big O of g of n. Big O of g of n means f of n is lesser equal to c of g into n, means at particular value of n0, before value of n0 we cannot identify which one is the smallest, matlab which function f of n or g of n is the largest or smallest. Here some value f of n become smaller and here it become larger. So, but after defining some value of n0, we can say it always satisfy the condition, that is f of n becomes lesser equal to g of n. Now here we take the example for big O notation, that is f of n is equal to 2n and g of n is equal to n. So f of n is equal to big O of gn if f of n is lesser equal to big O of gn, that means 2n is lesser equal to cn. Now when this condition is satisfied, if we take c equal to 2. Now here we take another example, that is f of n is equal to n plus 10 and g of n is equal to n. So f of n is equal to big O of g of n, that means n plus 10 is lesser equal to c into n. Now when this condition is satisfied, if we take c equal to 2, then it is satisfied. But before value of 10, matlab n0 value is equal to 10, then this function is always satisfied. For before and not value, we cannot say that f of gn is larger or smaller. Now the second notation, that is omega notation, which give a lower bound on algorithms. Let f of n and g of n to be non-negative function. If f of n is bounded below by some positive constants multiple of g of n, such that f of n is equal to f of n greater or equal to c into g of n for all value of n is greater or equal to n0. Now here f of n become larger than c into g of n after defining some value of n naught. F of n is equal to omega of g of n. Now we understand it by using some example. Here we take value a function f of n is equal to n plus 10, g of n is equal to n, f of n is equal to omega of g of n, means n plus 10 is greater or equal to c into n. If we take c equal to 1, then this function is satisfied. Now we take the another example for omega notation, that is f of n is equal to n and g of n is equal to n plus 10. So f of n is equal to omega of g of n is greater or equal to c into n plus 10. Now when this satisfy, if we take c equal to 1 half, then it is satisfied. But after n naught value is equal to 10, this function is always satisfied. Now the third notation is the theta notation, which give equal order, means same order, which give between the upper bound and lower bound. Now let f of n and g of n be a two non-negative function and there are some two positive constants used, that is c1 and c2. That means f of n is lesser equal to c1 into gn and f of n is greater or equal to c2 into g of n, means f of n become less than c1 into g of n and f of n become greater than into c of g of n. This condition is satisfied when after value of n naught, and representation that f of n is equal to f of n is between C1 into G of n and C2 into G of n means give the equal bound. Now here we take the example f of n is equal to n plus 10 and g of n is equal to n. F of n is equal to theta of g of n. F of n become lesser equal to c1 into gn. That means n plus 10 become lesser equal to c1 into n, and f of n is greater or equal to c2 into gn. That means n plus 10 is greater or equal to c2 into n, which is become true if we take c1 equal to 2 and c2 equal to 1. Now here also we take the another example, that is for omega notation. Function f of n has function f of n is equal to n square and g of n is equal to n. F of n is greater or equal to g of n. Here we take the different value of n, that is 1, 2, 1, 2, 3, 4 and 5. The function f of n become always greater than the g of n. Now here we take another example for big O notation, that is f of n is equal to n and g of n is equal to n square. So f of n become less than g of n. We test it by using different value of n, that is 1, 2, 3, 4 and 5. So f of n become less or equal to g of n. Now here we take another example for big O notation, that is f of n is equal to n square and g of n is equal to 2 raised to n. So it is by using different value of n, that is 1, 2, 3, 4, 5, 6 and 7. So here we see that if n equal to 1, then f of n become less than g of n. If n equal to 2, then f of n is equal to g of n. Now in the omega notation, f of n become less than g of n. So before the value of n equal to 4, we cannot identify which one is greater and which one is less than, but after value of 4 we can always say f of n become less than g of n. Now here we give some example for growth of rate. Try to arrange in some increasing order. Thank you.